Assalamualaikum warahmatullah and salam sejahtera to all of you. I hope everybody is doing fine with your family members in your hometown. Okay, please take care of yourself, especially during this restriction period of COVID-19 MCO. Okay, I understand it is not easy for some of the students to cope with all the e-learning things, but let's face this together. Please tell me if you have any problem with my subject, and maybe we can solve it together, and so that you will not left behind. Okay, I hope we can get through all this and you can manage to study and excel for all the subjects in this semester. Okay, so now we will go to topic 2 in this subject, which title of numerical solution of linear simultaneous equations and matrices. This topic consists of 3 subtopics, which is Gauss Elimination, Gauss-Jordan, and LU decomposition method. Okay, previously in topic 1, we have determined the value of x that satisfied a single equation or a function of x. So now in topic 2, we will deal with the case of determining the value of multiple x that come from simultaneous equations. Okay, if you can see here, it's a figure that's showing the available techniques that can be used for solving simultaneous equations. So we have Gauss elimination and LU decomposition and matrix inversions. So for this topic, we will mainly cover the naive Gauss elimination, the Gauss-Jordan method, and also LU decomposition. Alright, before launching into a more complicated systems, so there are simple methods for solving small systems. We will look at this method before going into depth for the other methods. Okay. Okay, now we will look at the available methods that can be used for solving a small systems. Small systems here means that we have lesser than 3 unknowns, okay, and we do not require a computer to solve this problem. Okay, first is the graphical method. For example, here for 2 equations, we can plot them on the Cartesian coordinates with one axis corresponding to x1 and the other one is corresponding to x2. Okay, because we are dealing with a linear system, so we will see 2 straight lines here. Okay, the second one is the Cramer's rule that can be implemented by using the concept of determinant. Okay, in addition, this determinant is actually can be used to evaluate the ill conditioning of a matrix. So here we have 2 sets of equation and convert to a matrix form of AX equal to B. So here we have coefficient matrix of A and the determinants of D. Okay, after obtaining these 2 matrices, we can solve for x1 using this equation and x2 using this equation. Right? You can look in depth to this method by looking at the example 2 in the lecture notes. Right, the last one is the eliminations of unknowns. This method is conducted by multiplying the equations by constants. Okay, here, so that one of the unknowns can be eliminated. Okay, this is called as a elimination step. Okay, this elimination step. And then the result is a single equation that can be solved for the remaining unknowns, which is the back substitute step. Alright. So as for the previous methods, you can see or you can study more about this elimination of unknowns method by looking at the example 3 in the lecture notes. Okay, these 3 methods are actually not in the syllabus, but I feel that it is important for you to know the basic of these 3 methods so that you will be more understand in the upcoming topics. Because some of them has the same basic concept with the methods that we will learn after this. Okay, you can refer to the lecture notes. I have given all the details, explanation and example for you to study and understand. Please go through it at least once. It is for your own good. Okay. The first method that will be covered in the topic 2 for numerical solution of linear simultaneous equations and matrices is the Gauss elimination method. Right? So the learning outcome for this subtopic is to solve a set of simultaneous linear equations using elimination method, and then understand the relationship between the determinant of a coefficient matrix and the solution of simultaneous linear equations, and analyze, identify, formulate, and solve related civil engineering problems using Gauss elimination method. Okay, this naive Gauss elimination method is designed to solve a general set of n equations. Okay, for example here, we have a set of equation. Start with equation 2.10, which is a11x1 plus a12x2 plus a13x3 and so on, equal to b1, and then followed by equation 2.11 and until the nth equations of 2.12. Alright, this method consists of 2 phases. The first one is forward elimination of the unknowns, where the set equations is reduced, alright, to reduce the set of equations. And then the second one is back substitution, where the unknowns are determined at this phase. Alright, this method does not avoid division by 0 as in computer program, because you cannot divide anything with 0. It will turn results to error. So that's why it called as naive Gauss elimination method. Okay, now we will look in detail on how to conduct the Gauss elimination method for solving the simultaneous equations. Previously, we know that this method consists of 2 phases. First is the forward elimination of the unknowns, and then the second one is the back substitution, where we can obtain the value of the unknowns. Okay, first of all, for the forward elimination step, we need to eliminate the first unknown x1 from the second equation. Okay, note here that we have equation 2.10. Okay, so this is considered as the first equation, and then 2.11 is the second equation. Alright, so multiply the first equation with the coefficient of a21 divided by a11. Okay, a21 is come from the second equation here, because we want to eliminate the x1 from second equation. And then the a11 is actually the pivot element. Okay, come from the equations that we refer, or called as pivot equation. Pivot equation is the main equation that we refer in this process. Okay, so and then subtract the result. Subtract the result of equation 1 multiplied by coefficient with from the second equation here. Subtract the result, and then you will get this long equation. Notice here that it starts with x2. because x1 is already eliminated in the process. Okay, so to be simple, this equation is simplified to a prime to 2x2 plus a prime to 3x3 plus so on equal to b prime 2. So this is the new second equation, and the prime represent that the coefficient is already modified. Okay, while this whole process is called as normalization. Okay, the division process is called as normalization. Okay, next, we are still in the first normalization process. Okay, because we are in the process of eliminating the first unknown of x1. But this time from the third equation. Okay, so same as previous. We have 2.10 as the first equation. And then we have this here, third equation. Okay, multiply the first equation with the coefficient of A31 divided by A11. A31 is come from the third equation where we want to eliminate the x1. While A11 is the pivot element that come from the pivot equation. As I told you before, the pivot equation is the main equation that we refer during the process. And then, as usual, subtract the result from the third equation. Okay, subtract the result of first equation divided by coefficient from the third equation, and then you will get this long equation, which can be simplified to a prime 32 x2 plus a prime 33 x3 plus blah blah plus a prime 3n xn equal to b prime 3. So note here that 3 is represent the third equation. Before this is a prime 2 2, that because the second equation. Okay, and the process repeats for the next equation. So in general, the first normalization steps in the forward elimination of unknown phase is eliminating the first unknown of x1, okay, from second equation to the remaining equations. Okay, here in general, we have to multiply the pivot equation with the coefficient of an1 divided by a11. Okay, a11 is the pivot element, and these equations, which is already modified, showing the prime on the coefficient. Okay. Okay, now we go for the second normalization. Right, where we will eliminate the second unknown of x2 from the third and the remaining equations. Okay, notice here we have a set of equations. 2.14 is the first equation, similar as previous. 2.15 is the second equation that has already modified in the first normalization process. And also 2.16 it's already been modified, and this is the third equation. Okay, we start with multiplying the pivot equation, which is the second equation, with the coefficient of a prime n2 divided by a prime 2 2. A prime n2, or in this case is a prime 32, is the coefficient where we want to eliminate the x2, while a prime 2 2 is the pivot element, come from the pivot equation. Then subtract the result from the third equation to get this set of equation. So notice that this equation start with x3 because we already eliminate x1 in the first normalization process and x2 in this process. So this can be simplified to a double prime 3 3 x3 plus so on plus a double prime 3n xn equal to b double prime 3. So the double prime shows that this equation has already been modified twice, and this is actually the new third equation. Okay, so in general, for the second normalization steps, the elimination of second unknown x2 has yielded to this set of equation. Okay, from the first a11 x1 plus a12 x2 plus so on equal to b1 until we get a double prime n3 x3 plus so on plus a double prime nn xn equal to b double prime n. So as I stated before, the double prime indicates that the element have been modified twice. So the procedure will be continued using the remaining pivot equations until nth normalization. So n is actually the number of equations in that particular set of equation. So here shows here is the general equation for all this process until a and n power n minus 1 prime xn equal to bn n minus 1 prime. Then we go to the second phase in the Gauss elimination method, which is back substitution to obtain the value of the unknowns. So previously in equation 2.21, which is a and n power of n minus 1 prime xn equal to bn power of n minus 1 prime. So when we rearrange that equation, we will get this to obtain the value of xn. It starts with the equation at the bottom. And then the result back substituted to solve for the value of xn minus 1. The remaining x can be represented by the following formula in general to get the value of xi. Alright. Okay, to gain more understanding in the naive Gauss elimination method, let us look at example 4. The question stated that by carrying 6 significant figures during computation, use the Gauss elimination to solve that set of equations. So notice that the question asks you to consider 6 significant figures during calculation. Okay, for the solution, as usual, we need to conduct firstly the forward elimination. Okay, for the forward elimination and first normalization. First normalization. Okay, we need to multiply equation 2.24, or we can call it as pivot equation because this equation is the reference equation in this process for the first normalization, by 0.1 divided by 3. Okay, 0.1 divided by 3, where we can get 0.1 here from the second equation where we want to eliminate the x1, and 3 is actually the pivot element. And then subtract the results of equation 1 multiplied by the equation by the coefficient. Subtract the result from equation 2.25. Okay, so you can get this equation as the new second equation. Okay, then still in the first normalization process. Okay, first normalization process. We need to multiply equation 2.24, which is the first equation from the previous, by 0.3 divided by 3. 0.3 here is actually the coefficient from the third equation, and 3 is the pivot element. And then subtract the results from the equation of 2.26, which is actually third equation from the previous equation, and eliminate x1 to get this set of equation. Okay, and then next, for the second normalization, the pivot equation is changed to the second equation. Remember that for the first normalization, the pivot equation is the first equation. So this one, the pivot equation is the second equation. And the pivot element also changed to this 7.00333. Okay. For the second normalization, multiply equation 2.28 here with the coefficient of negative 0.19000 divided by 7.00333. Okay, this is the pivot element as shown above. And then negative 0.19000 is the coefficient for x2 where we want to eliminate. And then subtract the result from the third equation, or equation 2.29, to eliminate x2. And reduce the system to an upper triangular form as this. Okay, upper triangular means here is 0, 0 and 0. Okay, completing the forward elimination process, we will go to the second phase, which is back substitution. Okay, solve this equation by substituting x3 in the equation of 2.32 previously. So we start from the below to determine x3 equal to 7.003, and then back substitute into equation 2.31 to determine x2. Okay, to determine x2. And finally, from equation 2.33 and equation 2.34 can be substituted into equation 2.30 to gain x1. Alright. Notice that the results obtained previously are close to the exact solution given here. Okay, the exact solution is x1 equal to 3, and then x2 equal to negative 2.5, and x3 equal to 7. This can be verified by substituting the results that we obtain into the original equation sets. Okay, the original equation set is given here. So we put the result that we obtain inside the equation, and then we compare. So 7.85 is definitely the same. And then we got negative 19.3001 for the second equation, which is close to the original equation. And for the third equation, we get 71.4003. That is also close to the original equation. Although the technique of eliminations suit for implementation on computers, sometimes some modifications are needed to obtain a reliable algorithm in the computer. So there are pitfalls that one should aware of before writing a general equation or general computer program. Here, The pitfalls that we will discuss are division by zero, round-off error, and ill-conditioned system. So the first drawbacks is the division by zero. During both the elimination and back substitution phases, it is possible that a division by zero can occur. For example, if we use naive Gauss elimination to solve this set equation, we can see here that the pivot element is 0 for the first normalization. So when we have a pivot element equal to 0, any division could return an error result. So there are techniques that can develop to avoid this problem, which is called pivoting. This will be discussed later in this topic too. The second one is the roundoff error. Okay, there was a slight discrepancy in the result for X3 in example 3. The relative true error amounted is 0.00043% from example 4. So if you see here, results for example 4 compared to the original equation, so there's a slight discrepancy. But this error would have been higher if lesser significant figures were used. Okay, to see this, repeat the calculations in example 4 by considering only 4 significant figures. Okay, note that for example 4, we consider 6 significant figures. As a result, a higher relative true errors were obtained if 4 significant figures were used instead of 6 significant figures. For example, as stated previously, for the unknown of X3, the true errors if we use 6 significant figures is 0.0043%, while if lesser significant figures, which is 4, used in the calculation, we will get higher true errors, which is 0.02854%. This shows that a more accurate result can be obtained by using or by considering more significant figures in the calculation. The third drawback is the ill-conditioned system. It is where a wide range of answers can approximately satisfy the equations that actually could mislead into believing that incorrect solutions are correct. So firstly, we look at what is well-conditioned system. Well-conditioned is where a small change in one or more of the coefficients results in a similar small change in the solution. For example, if we have a change in the coefficient, this is the coefficient, will result, and also a small change in the solution. This is the solution. Okay, and then the determinant of the matrix is equal to non-zero. So determinant not equal to 0. You can see further the difference between ill-conditioned and well-conditioned from example 7. While ill-conditioned system is when 2 or more of the equations are nearly identical. So for example, if you look here, the line is nearly parallel. Small change in the coefficients result in large change in the solution. Okay, let's say we do a small change in the coefficient, it will result a big change in the solution. Alright, and the determinant of the matrix of this ill-conditioned system is nearly to 0. Okay, we can see this condition from example 7 and example 8 in the lecture notes. The next one is singular systems, where it's actually under the ill-conditioned system criteria. Is when a systems have an identical slopes, It's either no solution or an infinite number of solutions. For this system, the determinant is equal to exactly 0. Alright. Although the elimination method has the drawbacks, but there are techniques for improving the solutions. So the following techniques stated here can be incorporated into the Gauss elimination algorithm to avoid the drawbacks discussed in the previous sections. So these techniques consist of use of more significant figures, pivoting, and scaling. The first technique that can improve the solutions is by using a more significant figures. Okay, it's been proved previously that using a higher significant figures will result in more accurate results. But this will cause a great computational work and requires a large computer memory. So we need to think about this before using more and more significant figures. And then the second one is pivoting. Problem will rise if we have a pivot element equal to 0, because normalization step leads to division by 0. Okay, and problem also rise if we have a pivot element that has a value near to 0, because it could lead to round-off errors. So as a solution, during normalization, switch the row, okay, that have the largest coefficient to become the pivot element. This is called as partial pivoting. So this could avoid division by 0 and minimize the round-off errors. Okay, the pivoting method can be seen in detail in example 9. The third technique is called scaling. This can be done by multiplying the equations by a constant value. Okay, this technique can minimize round-off errors. For those equations that have much larger coefficient than others. Alright, as long as each equation is consistent, the system will be technically correct and solvable. However, the use of differing units can lead to coefficients of widely differing magnitudes. This could have an impact round-off error as it affects pivoting. Alright. Example 2 shows the detailed calculation on the effect of scaling on pivoting and round-off errors. Okay, the next subtopic is determinant evaluation using Gauss elimination method. This method is actually based on the fact that the determinant of a triangular matrix is the product of its diagonal elements. So what are the diagonal elements? Are this one, A11, A22, A33, and so on until A and n if you have n sets of equations. So the determinant of the previous equations or the previous matrix is equal to this. D equal to A11 multiplied by A22 multiplied by A33 and so on until A and n for n numbers of equations. The validity of this formulation can be illustrated for a 3 by 3 system. Okay, we can calculate the determinant equal to A11 multiplied by A22 times by A33 minus A23 times by 0, which is cancelled. And then minus with A12 multiplied by 0 times by A33, cancel. And this also cancel. And then plus with A13 multiplied by 0. So this is also cancel. Thus, we can evaluate the minus or the determinants equal to A11 times by A22 times by A33. Take note that determinant will not change in the forward elimination process that bring results in an upper triangular system. Okay, the determinant evaluated at the end of this step will equal to A11 times by A prime 22 times by A double prime 33 and so on until A and n power of n negative 1 prime. So the superscripts here indicate the number of times that the coefficients have been modified. If the program employs partial pivoting, there is a slight modification on this equation. Okay, for this case, the determinant change sign every time a row is pivoted. So we need to multiply the equation with negative 1 power of p. P here represents the number of times that rows are pivoted. So we need to keep track of the number of pivots that take place during the computation process and then use to this equation. Now we look at a simple example of finding determinant using Gauss elimination. Okay, here we have a coefficient matrix of A, and then after conducting the forward elimination process, the upper triangular system of A is equal to B. Note here we have zeros triangle below, so we call it as upper triangle system. So since determinant A equal to determinant B, thus the determinant B is equal to 25 times by negative 4.8 times by 0.7. So the answer is negative 84. Okay, to test your understanding in this topic, I need you to do the exercise 1. Okay, the question is the nodal displacements of a portal frame U, V, W, and Y can be found by solving the equilibrium equations in metric form of AD equal to L as follows. So using the Gauss elimination method, solve all nodal displacement of the portal frame if the loads of P, Q, R, and S equal to negative 1000 kilonewton. You can get the answers from the lecture notes to be your guidance in doing this exercise. Okay, thank you.